How's it going, everybody? I feel like there's a little, I don't know, maybe it's just my own proprioception, but it feels like there's a hushness to us, and I'm wondering if it's several things. If it's like the hard homework, if it's the Jayhawks performance in Manhattan, if it's other things, if it's the grind of the semester, you're like a couple weeks from spring break, and this class just won't stop asking things of you. I get it. I'm sorry. Hopefully it gets better. I hope that you're learning from this class. What I will say is that the part that was the most difficult, I think, in the class is over. That homework that you just did and redid was the worst. Period. Bar none. Homework. And I knew it was going to be that way when I designed the class to do this every other week homework thing. But you made it. And my big picture with all that is still trying to fit in why it is we do everything that we do. And so having a picture of what a covariance matrix is, of what a likelihood is, those are two things that show up all the time. They're going to show up today, although we're not going to talk about them. It's not going to be the bulk of what we're talking about today. You'll see them today. So it's kind of the underpinnings for what we do. So it stinks to have to go through it. It's not easy, but at the same time, do you feel like you have a good concept of a covariance matrix? Perhaps, and maybe a distribution or two and how we find likelihoods? If you have that, then I'm happy. That's where we want to be right now. How about path analysis? How does that feel for you? It's regression on steroids, right? If you can do one regression, you can do 10 of them all at once. That's how I feel about it, right? There's certain other terms that show up, exogenous and endogenous, but pretty much it's the same thing. I wanted to talk about a couple things I failed to mention last week. Number one, in the homework starter file that you'll see online, this is a picture of it. The data this week have missing data, and in the data file they're denoted by a dot. And R has, in the function, I put this function, so if you use the starter file, it protects you. It'll work. It'll keep the missing data as missing, but R treats missing as the letters NA. So when you read in your data, most of the time, if you're reading it from some other package, NA is not missing, it's just a character. So you have to tell R what really missing happens to be, and so this is where this NA.strings equals shows up. So if you're ever reading in data of your own to R and you have missing that's not NA, but maybe it's a dot, maybe it's a -9, maybe it's -99 or so forth, you just take this in this quote and put in what is missing. If you have more than one missing term, then you can put, R has a function that's a C function. So maybe you have -9 for some and then periods for other. It looked like that. You would put that in your NA string spot. So that way when R opens the file and reads it, whenever it encounters what's in the quotes, it just changes that to its internal storage as an NA. So this week's homework had you not use the starter file to read in the data, which is cool too. I didn't tell you about that. So the dots might have caused issues. But if you use the starter file, you're fine. It will treat them as NAs. Okay? Questions? Good. Second thing I'd like to talk about. So we have this homework that was a monstrosity, and we have path analysis now. And I want to connect the monster homework that you just did to the path analysis. I didn't really do that last week. I've sort of glossed over it. But one thing that I keep talking about, in homework 2, we said we had tried out, particularly in part 2. Part 1 was essentially here's what a likelihood is, and here's how we plug in numbers and get likelihoods back. Part 2 was model comparison. And in our path analysis lecture last week, we did some model comparisons, essentially, right? We fit a model, and we would compare it with the alternative model, H1, the unstructured model, and it always shows up. The reason why we can do that is the path analysis itself makes very specific assumptions about what the covariance matrix should look like. And I didn't get into the tech. I don't want you to do, there's so much with path analysis anyway, I don't want to add to this. This is a conceptual thing. There's nothing going to be tested on this. I just want you to think about it. Right? We talk about this idea that everything that we're doing is a testable hypothesis. We mentioned the word causality at the end of last time, where we said you hypothesize this path model, you hypothesize all these relationships, and if the model fits, causality might be one of the things that you get out of it. If the model doesn't fit, you reject it, right? That idea of rejecting and or hypothesizing and then seeing if the model fits implies really specific structures to your data. And so when you put a path model together, here's a 3-variable path model. This is a slide from my time I taught this course at Georgia in 2012, where I had 147 slides on path analysis, which was ridiculous, and they really meandered all over the place. It took 3 weeks to get through. Right? I've tried to take the bits and pieces of them and put them in different order in this class and so forth. But these are 3 variables from the analysis last time. So if you think of those 3 variables that these slides show you, if you really want to know the technical side of it, I don't want you to know the technical, I want you to know the big picture. Those 3 variables show up in a model that looks like this right here, if I can zoom in. So there's our 2 equations, right? We're predicting, in this case, college credit hours and math self-efficacy. And college credit hours and math self-efficacy are the endogenous variables. We have high school math credits or math courses as an exogenous variable. And here, college credit hours is being predicted, but then it goes on to predict other things. So if we were to take these series of equations, we could reduce the number of lines we have into a general form, a general matrix form. And that's where this shows up. Now, I don't want you, again, big picture, don't focus on the nuance of this. Why I'm telling you this is that each of these terms show up in a matrix, and then those things show up in parts of your covariance matrix that we're predicting, right? So what we're doing is we're hypothesizing these 2 models. And once we hypothesize them, what we're saying is if our hypothesis is to be confirmed, or if we don't quite reject it, our covariance matrix for our data, in this case there's 2 endogenous variables and 1 exogenous. So let's imagine we have all in the likelihood, so 3 by 3. That thing will have a very specific structure based on all the model parameters that we see here. So the Kaplan book I mentioned as being very technical, very hard to get through, but this is sort of me trying to parse through that. So I just want to show you how these beta weights show up as covariance terms. Believe it or not, they are covariances, or they are parts of covariances that go into it. So here's a really weird equation. Whenever I used to see this when I took my path analysis classes, and let me tell you, I didn't learn it all in my classes. This came to me as a professor also. You never stop learning. That's the cool thing about this job, right? You keep learning and keep getting better. I saw this and I thought, whose ridiculous idea was that? We have y on one side of an equal sign and we have y on the other side. But we have that because y's are dependent variables, and in the path analysis, our dependent variables can predict other dependent variables. So if y is this vector of the 2 endogenous things, we can have it show up here, but when it's not predicting one of them, we can make the beta weight for it equal to 0. And that's what this B matrix, or capital beta, happens to do. So, so this is this ugly set of equations. We have the regression weights that multiply the endogenous variables when predicting other endogenous variables in B. We have the regression weights that multiply the exogenous variables in this gamma matrix, capital gamma. We have all of our intercepts in alpha. And then all of our residual terms, in this case we'll have 2 error terms, residuals. I think that's a xi. My wife calls that squiggle 1 or something like that. So that works. So those are all the matrices, and I tried to define each of them in this slide here. Let me see if I can make this work, where we can see this. Those are all the matrices. So here, for instance, y has 2 endogenous variables in it. There's only 1 exogenous variable. Alpha has the 2 intercepts. This beta matrix only has 1 term, but it's the slope that shows up multiplying the other endogenous variable in the equation, the second row, which is like the second equation for it. So all of these matrices put into that linear equation give you these two equations back. That's what those are trying to say. Okay? So the other thing we need to note is that our residual terms have an assumption that they are multivariate normal. There's two of them, so there's a bivariate normal. We called this matrix the R matrix last time. They have a residual covariance matrix, sometimes called psi. I think it's 2 by 2. There's a residual variance for the first one, a residual variance for the second one, and then a residual covariance between them. And those all show up in psi. Okay, so we're running out of alphabet. We're running out of Greek letters. All that goes together. Here's putting it all together if you want to work through it. More math. The other terms, we have the exogenous variables have a covariance matrix usually. This thing, there's only one in our analysis, so there's only one variance in it, so it's like 1 by 1. And when we put it all together, here's what we get. For every observation, we get a predicted value, their mean vector, right? What we're doing in Lavon and what we're doing in our programs is just what you did in the first part of homework 2. We need a predicted mean vector for each person, and we need a covariance matrix for each person. So for the mean vector for each person, we use, here we actually, this is the overall mean, but if we were to replace mu with a person's data, x, here, we would get the mean vector for each person. This big covariance matrix, as I look at that, I actually think that might be a little bit incorrect because I need to get the endogenous variables in there too. So anyway, point being, there is a formula for the mean vector. That's the big, we're to try to be 10,000 foot here. Then there's a formula for the covariance matrix, and it breaks down into parts, right? The upper part is, let's put the endogenous variables in, right? So here's two endogenous variables. They're covariances. Right, their variances and covariances should follow this ugly looking structure. If that's not one of the longest matrix products you've seen, let me know. Have you seen this before? Probably not. But what does that mean? Okay, so beta has the regression slopes for endogenous predicting other endogenous. Gamma has the regression slopes or beta weights for exogenous predicting these. Phi is the exogenous variances out there. What I'm trying to say is that once we specify all those equations, what we're doing is setting up a very specific structure for the endogenous variables. Take a look over here on this exogenous part. By comparison, that's just one matrix. That's a saturated matrix for the exogenous variables. It's just the variance that shows up there. And then the off diagonal, we end up getting some kind of weird product of endogenous versus endogenous slopes and exogenous terms. So big picture, we specify all these paths in our path model. It says, okay, if this is true, we should get a covariance matrix that we can form based on the regression slopes, the endogenous and exogenous variances. The endogenous regression slopes, exogenous variances, endogenous variances, and exogenous regression slopes. With all those terms, it should look like this. And if it doesn't look like this, right, the way that we test it is we compare it with the saturated model, where every variance and covariance gets estimated. Right? If it doesn't look like the saturated model, we reject it. If it does, we keep it. So why we talk about model fit being important is that if you think about all this ugly math up here, let me see if I can put in variables here. This right here is a 3 by 3 covariance matrix. This is what we should observe. This is the saturated models version for these three variables. And this is this unstandardized, the raw residual between what our model says this should be and what we actually have. Right? So we're off a little bit. This is actually a pretty good fit. With three variables, we end up getting almost exact fit. So we should have exact fit. I ended up taking off one of the residual covariances to make this have not exact fit. But what we'll see is what are all those parameters we're trying to do is in that nonlinear, that ugly looking matrix equation, they're trying to take these 6 numbers and parse them into each of the beta weights. And when we're off a little bit, right, it doesn't like being off. It tries to move the number over, stretch it, if you will, to cover for it. And so model misfit shows up here this looks like the model fits. If we were to observe really bad misfit here, our beta weights would be the things that suffer from it. They would be twisted in different ways because they're certainly stretched to try to cover the misfitting parts of the analysis. So going back to all of what we're doing with the covariance matrix and why I'm trying to talk about this, when your model doesn't fit, it doesn't fit, that lack of fit shows up in your estimates. And the estimates aren't what they really should be should the model have fit. Right? So when you look at the residual covariance matrix, when you look at the difference between what your model predicts the covariance matrix to be and what your saturated model version is, it sort of gives you information as to, wait a minute, I need some type of term that shows up in here to make it fit better. So, big picture, again, model implies a structure that we test. Right? Model implies a structure that we test. And all the things that we've been doing in this class has been trying to build to that part. Now you know covariances, now you know covariance matrices, now you know saturated models, now you know model comparisons. We've got all the tools there. Believe it or not, factor analysis that we're going to talk about today describes a very similar, it's a similar idea, right? Similar structure. So we're going to see that. Questions on this? Is it making sense? Sort of? Again, if you wanted me to go and prove this to you, I can tell you the math you'd have to use for it. I can't do this off the top of my head. I have to look this up. I don't know anybody who has that as a tattoo either. So it's always a good thing to do, tattoo equations. I've actually met some people in my field that have tattoos of equations on them, believe it or not. Neil Kingston? No, I'm sorry. I'm joking. Trying to be obviously joking. Anyway, yeah, I would be in trouble for that. No, anyway. So big picture, we're good. This is not easy stuff at all, right? But it is pretty regular. There's a lot to it, but there's pretty much, it's regular, right? Covariance matrix. If you're assuming these things are continuous and have these errors that are normally distributed, so you get conditional and multivariate normal, this shows up. All right, then let's go to today's lecture, shall we? Any other thoughts or questions before I throw this on? Today we're talking about the next part of structural equation modeling, which is confirmatory factor analysis. How many of you have done factor analysis before? I think a lot of you probably have. Somehow. Exploratory, maybe? This gets into psychometrics, which is really interesting. A lot of my program is built on testing in psychometrics and developing scales and measures. And have you ever taken a class in psychometrics? Anyone heard that word psychometric before? So there's a baby coming in my life, and on my daughter, her birth certificate doesn't list me as professor, it lists me as psychometrician. So I self-identify as a psychometrician, and on this soon-to-be-born child, whose name that only is disclosed to very select people so far, I already filled out the paperwork. I'm psychometrician on there too, so got to keep this real. The idea of psychometrics is the measurement of things we really can't observe. So factor analysis is part of that, and confirmatory factor analysis takes that idea and maps it onto data that fit a very, and the label confirmatory factor analysis goes with data that are, again, multivariate normal itself. So we're going to get into confirmatory factor analysis. Structural equation modeling is what we call path analysis with latent variables. So we're going to see that latent variables show up in our model. And this is like our first day of class this year, where I had that example with happiness that was something we couldn't directly observe, even though we did test items. The hard part in thinking about factor analysis is a lot of times we take a scale and that is our observed data, right? We take a scale, we add up the items, and hey, this person's happiness is the sum of these items. And the way we have to think about this in terms of a statistical or psychometric approach is that happiness is not the sum of those 5 items. That's a question, that's an empirical question, that's an assumption we're making. All that we've observed are 5 items. Whether or not we can synthesize those into a factor is a testable hypothesis. And that's what this portion of the class is about. It's seeing whether or not we can take 5 items and say they measure happiness, or whether or not we'd have to change the configuration, or maybe we have more than one version of happiness, or there's lots of ways that this goes. So you'll see what we do in this class in the next 3 weeks is we take a detour from path analysis. Although this is really path analysis, it is multiple equations all at once, but these things that don't exist show up there. So to do this, just keep remembering, if you could hold on with me here, there is no score. Right? There is no score, there is no scale. Nothing. Right? All you have are the items of the test or the survey that you have. That's it. Right? I know it's very common. In fact, in my field, everybody wants to just add things up or get a what we call a theta, an ability estimate, right? Your GRE score. I'm going to tell you right now, there really is no such thing as a score. Your score is a hypothetical thing that we can't observe directly. It's like missing data. So all we get for you is our best guess as to what the distribution of your score might be, right? So if you could bear with me on that, right? Your response is the only thing we've observed, and that's what we have to work with. Everything else is hypothetical, and then we can put the math together to test it to see if we should be doing that. All right? There is no score. Now listen, we all go and do this all the time. We add up things, we put them in the model. There is no score. That's what we're thinking about. Cool? Is there a score? No score. No score. No score. There is no score. That's right. All right. So we're going to use, to do this, to try to estimate things that don't exist, we have to do certain policies, certain types of procedures. We have to specify a model. It's going to look very much like a path model. We have to identify the model. Remember that word last week, identification? We talked about counting. The T rule, counts, add things up. Yeah, that's good. We also talked about local versus global identification and so forth. That gets a little bit different in here, mainly because for our model, we have to go a step further than counting. We have to go and set certain things in the analysis. Right? So if there is no score, let's keep thinking about this happiness variable. If there is no score on happiness, right, but we're going to try to measure it anyway, what we have to sort of anchor it is what scale is it on? Right? What's its mean? What's its variance or standard deviation? Right? So we have to go a step further than counting up the number of parameters we have. We have to actually go and say, yeah, we're going to go find a way to specify its mean, or we're going to go find a way to specify its variance. So that's what the extra step for this is. It further makes the case that these things really aren't real, right? Because we have to go and tell you what its distribution sort of looks like. The next step that we've done follows from path analysis. Actually, all of these parts come from path analysis. I'd say all of these showed up in path analysis, but this is a new thing. We check the model fit, and within if model fits, we interpret our example. All right, so all the stuff you've seen before about model fit still applies. Mainly, again, if we assume the factor is continuous and normally distributed, and then the error terms are continuous and normally distributed, then we can still do the same type of model fit assessment we've been doing up until this point. So we're going to do a single factor today. We're going to do a single factor next week. And then the week before spring break, we're going to talk about multiple factors all at once. And the reason for that is purposeful. It's a lot easier to figure out whether a single factor fits your data than it is to go to multiple factors all at once. That doesn't guarantee you that multiple factors will fit all at once when you go from a single to multiple, but it makes it easier to figure out where things might be off a little bit. So we're going to talk about single factors all at once here today. So, questions for today. How is factor analysis like path analysis? How is it unlike path analysis? What model constraints have to be made to identify a factor? What data characteristics must be present to identify a factor? And what are standardized factor analysis coefficients? We heard about standardized coefficients last week. Remember those? Those are like saying whenever you're switching from units of x, or excuse me, units of y per units of x for a beta weight, you're saying it's standard deviations of y per standard deviations of x. That's still going to be apply here, although we get the little caveat that standard deviation is something that we might actually set arbitrarily for the factor. So today's class data. For those of you who've been in my classes before, these data are familiar to you. Those who aren't, welcome. I'm pretty sure that people like Hong Ling can come up here and tell the story of these data, since you've heard it over and over again. And Lou and Dan and Yang, I mean, Aisha, the people who've been around me a while. Hope I'm not leaving any of you out. We're going to use 5 items of a scale called the Gambling Research Instrument. And the story of this was I was in grad school a very long time ago, and I joined a lab. I'm in quantitative psychology, but one of my professors is studying gambling behaviors. And so he had a grant where he wanted to go and survey gamblers from a casino boat in Illinois. So there's a casino boat in Peoria, Illinois, named Paradise, or it used to be named Paradise. I don't know if any of you know Peoria or Paradise, but this is, he had access to this boat. His grant actually came from a consortium of gambling, the gambling industry, let's just put it that way. It was their way of making sure they were concerned about pathological gambling, right? We want to make sure that those who are giving us money know when they have a problem. Right. I'm saying that tongue-in-cheek, but at least they tried. Helped give me some opportunity. So we went up to this gambling boat. We were able to have access to the security camera. So we wanted to find people who had gambled enough on a roulette table to bring them off of the boat to see if they were willing, and have them play roulette on a computer in our lab and see if there's something about the way they played that we could identify whether they've got pathological tendencies, right? So it sounds fairly feasible. It was sort of the grant itself was really built weird. To get the people off the boat, we had one of the graduate students in the lab was gambling with them, was sitting at the roulette table and keeping track of who was there, and with a sort of trying to be nonchalant with a watch. They'd been there 30, 45 minutes, can't remember how long it was. Kind of, okay, that's the person we want to ask. And then we had another grad student off of the table just sort of watching. Sounds like we're doing like counting cards, right? And this person, when the gambler would get up, we kind of, hey, this is the person. And then they'd go and walk up to the person, excuse me. And the next thing you know, they're like, well, the pitch is, hey, would you like to come with us off of the boat? You could win up to $250 to do this study that might take an hour, which you could then go give back. So that was the pitch. But to play at the table, we had to act like we were gambling. So we took some of the grant money and we were actually gambling it. All right, which is the most awesome story ever, right? And we all, the lab instructor, the professor, he gave us all a chance to at least spend a night on the roulette table. So yeah, here's some money, just gamble with it. So this is where I give you the caveat that this grant money came from the gambling industry anyways. It's like we're not super unethical. We're sort of giving it back to them. We were told that if we won, we would just not have to don't tell anybody that we won, just make sure that we lost everything, right? I went through my money pretty quick. Anyway, that was my first experience gambling. With the exception of 5 minutes in Vegas on the way back from looking, this is back when gas was cheap and I couldn't afford a plane ticket. So drove out to grad school to find an apartment. I stopped into Vegas on the way back to California. Put $5 in a video poker machine. I thought, I don't know why people do this. So then I did this. I'm like, now I get it. And so I went back to Vegas with a vengeance. But thankfully I've calmed down from there. I don't like gambling anymore. But no, the irony with this is studying gambling got me into gambling. So I digress. These are 5 items from a gambling research instrument. This lab was not all that productive in terms of scholarly activity, as you might imagine. And the other professors sort of halfway joke, this is kind of like the last grant this guy got before he retired. And when he retired, he really retired, not like some of the professors who kind of become emeritus. You still see them around. They just don't go to faculty meetings or teach. Anyway, they're like, yeah, he just wanted the grant where he could go gamble with the grant money. Okay, that seemed to be about it. So not a lot of papers about this, but here's one. We have 5 items from it. What we'd like to do with these 5 items is to build a survey that talks about somebody's tendency to want to gamble. Right? So what we would call this is like a gambling factor. Right? These items are all Likert type items, so there had a 6-point scale where 1 was strongly disagree and a 6 was strongly agree. and different versions of how strong you are in the middle. The 5 items are: I would like to cut back on my gambling. There are a few things I'd rather do than gamble. If I lost a lot of money gambling one day, I would be more likely to want to play the following day. I enjoy talking with my family and friends about my past gambling experience. See, if you're like my friends, I was just telling you my past gambling experiences. And then I find it necessary to gamble with larger amounts of money than when I first gambled, for the gambling to be exciting. These are all actual items from it. The items itself were built to measure pathological gambling in general. We had if you look in the Diagnostic and Statistical Manual of Mental Disorders, the DSM, in the impulse control disorder section, there is a definition of pathological gambling. It's right between kleptomania and pyromania. Right? It's something that is an impulse. It's hard to control. And there are 10 criteria listed to be defined as or to be diagnosed as probable pathological gambler. You have to have met 5 of these. And they run in severity from somebody who's preoccupied with gambling to somebody who's committed illegal acts to finance gambling, right? So you can think about there's a big difference in people who think about gambling and then people who actually go and break the law to finance it. So today's class is a little snippet of it. Pick 5 items. We actually had 41 items, and we tried to measure all 10 of those as if they were their own factors themselves. The thought being that if we could sort of get kind of a scaled score for each person on each of these factors, that we might be able to do research as to what predicts how related they are and so forth. Didn't really go anywhere. Oh, there we go. I underlined these things in my slides. So, let's see here. Our sample, we had 112 people from most from the actual casino. I did publish a paper on this. It was in a quant journal on quantitative analysis, a little bit different. And they insisted I go get a bigger sample. And so I did. They're like, I went and grabbed 1,192 college students from what I call a rectangular Midwestern state. We actually live in that rectangular Midwestern state. But, it's how you read journal articles, it says a southeastern state or whatever, That's my way of saying it. Yeah, a rectangular Midwestern state. That narrows it down, right? Which is a terrible idea, because most of the college students I surveyed here on campus back in 2005 were 18 to 20. They were the undergraduate subject pool in the psych department, and most of which had never set foot into a casino, or if they had, it was not very long. So it was we're a little ridiculous, but we're not going to let that stand in the way of the good story. We're just going to use all 1,304 subjects to analyze these data. So we'll start with the conceptual overview of factor analysis. What we're trying to do, again, remember, we're trying to measure gambling tendencies. That's our scale. That's our factor. It doesn't exist, but we have these 5 items that we'd like to see whether or not they measure. So that gambling tendencies is a latent trait. It is unobservable, right? It is an ability, a characteristic. It can be anything. Intelligence, extroversion, political idealization, name it. But when we go and assess whether a latent trait exists, the same process holds, right? Our latent trait, are saying these 5 items are measuring gambling, is a hypothesis. It's a very specific hypothesis that we're going to test using something called a measurement model, right? So I look at psychometrics like I look at a lot of other empirical sciences, empiricism. We're trying to collect data to disconfirm our hypothesis, right? So we're testing a hypothesis, and in this case, we're saying, yeah, these 5 items, we're hypothesizing that they measure gambling. This is no different from how many of you work in the CETE, is it an RA? So you have like your CAP program, you have like where we assess students at the end of grades in Kansas and Alaska. You have CPAS, is it, right? So all of those, we have a test we give out, and we send out test scores. All of those test scores represent our best guesses to somebody's latent trait, and in theory, that's a testable hypothesis as well, right? Anytime you look at a study and they've got a latent trait Remember, it doesn't exist. It's hypothesized. That's it. It's tough to undo because the score is so natural. There is no score. So we use a measurement model. It looks like a path model, but in there shows up the actual thing that doesn't exist. We say, okay, if this thing were to exist, what would it do statistically? And that is what the measurement model tries to specify. We'll see that in just a little bit. But it links the measurement model, and any measurement model necessarily links the observed data, the things you did observe, whether it's correct or incorrect responses to a math test, or it's these 5 gambling items, to the hypothesized trait itself. Saying, if we could have observed this trait, how would we have used it to predict these responses on these items? Okay? And that's always the fun thing about measurement models. It's funny, it never really dawned on me much until I started doing research in my own career, but it's almost like saying, imagine that you could observe what you're thinking you're measuring directly, right? If we could observe somebody's true state of how much they want to gamble, what would we do statistically to predict these 5 items with it, right? Put it in a path model. We predict them all at once. It's multivariate regression, right? That's it. That's a measurement model for you. So, latent traits get measured with multiple observed items. That is one of the things that we have to do. We cannot necessarily observe a trait or test a trait if we don't have multiples of items. How many, we're going to talk about in just a bit. Right, so we can't just say one item is a trait. It's not a trait, it's an item. Right? And so our models, actually, well, we'll get to that in just a bit. So the models themselves go by certain names. You know me in labels. I hate the name labels, but what we're doing in here is something called confirmatory factor analysis. And that usually pretends that our responses are continuous. So those 5 categories of Likert scale data, we're going to pretend those are continuous today. I see a look. Jennifer, does that make you worry? That does not seem right. No, that is exactly the biggest problem with it. So if we don't want to do that, if we want to treat them as categorical, we use the same idea, but now the model names change. They're called item response models. Right? Many of you have taken IRT. Some of you will take it next year with Dr. Skorupski. Right? We're doing the same thing, literally. The only difference is that we assume different things about the structure of the items. And one of the bigger problems that people have with the idea of factor analysis or confirmatory factor analysis is that we assume items follow continuous, are continuous. We have these 6 options a person can pick from, and if we put an integer to each of them, maybe we take the strongly disagree and say that's a 1, and the strongly agree that's a 6, and all the points in between is one integer interval away. How on earth can we assume that to be a continuum? Right? That's a, yeah.
What model do we need to use if you have both?
If you have both, there's really no name for it, but you could put both of them together in the same analysis. So they will absolutely work together. It's sort of mix and match. That's a good question. But yeah, our models themselves, we have to assume these continuous things today. We're going to assume it. Once we assume it, then we can start to bring in this multivariate normal distribution around. But that's a tenuous assumption. And that is sort of the discrepancy. So have that in the back of your mind. We're going to talk about that probably a little bit more next week. But have that in the back of your mind. Do these data really continuous? Right? But most people are like, it's okay, it'll be fine. Sorry, most people in the social sciences will be like, it's okay, it'll be fine. Unless you have like 2 categories, and then that's totally taboo. Like if you have 3 categories, that's terrible too. You can't. You got to use IRT for 3 categories. 4 is where people are like, maybe, I don't know. So, do you know what I'm talking about? Do you have data like this? All right, and pretty much all data. You should see some of these gambling data, right? Mostly everybody strongly disagrees. Yeah, have you gone to, have you broken the law to finance, if you run over your grandma to get her retirement account? No, strongly disagree, right? So it may look like we have 6 categories, but in reality, our data really only have 2, right? Or maybe 3. So anyway, we have to do that. But as we had just mentioned, the bigger picture is this: the definition and the way that we look at measurement models in a contemporary sense is that we think of each dependent variable, like each item as a dependent variable in a path analysis that we can specify a different assumption for if we need to. So sometimes we may have dichotomous items, and you go and say, okay, this follows a categorical distribution. Sometimes we'll have continuous things. So, okay, yeah, these are going to be close enough to normal that we'll use normal distributions. And then maybe we have somewhere that's not either, right? Maybe we have a count or a zero inflated count, the number of cigarettes you smoked, this year, right? That's clearly something where most, I think, 28%, 26% of the general population of the United States smoke. So we would observe, if we had a sample from that, most people would say zero. Maybe people who do smoke would have some number that would be a continuum for, right? So all of these types of analyses, when we think of the unit of analysis as being the raw data itself that we observe, we can specify a distribution for. We're not going to in our class up until the end of the class, mainly because if we can at least pretend these are continuous enough, then we have a nice research tradition of 100 years to fall on. If we can't, then that research tradition starts to break down, and we have to worry about how we assess model fit, and becomes a mess. Questions? Okay. Exciting? Yeah, I don't know. I love this stuff, but then again, I'm crazy. Other terms that show up, structural equation models, I mentioned this before. These are simultaneous linear models, or like multiple regression lines, if you will, with observed and latent variables in the measurement. Right? Latent variables are in measurement models. Observed variables are just the variables themselves. And we typically reserve the name path analysis for simultaneous regressions or simultaneous equations when all variables are observed. Like last week, we pretended everything was observed. Probably not a good idea. Okay, so our CFA model is exactly what I was trying to get out of my mouth a few minutes ago. If we could observe the factor, which is this F term right here. I can grab it, but I can't draw on it when I do that. Right? So let's imagine we have this gambling factor. We're just going to call it F. That's our factor, right? If we could observe it, if we had some type of amazing way of quantifying this, what we would do with the gambling factor is say, okay, we have these 5 items. If the gambling factor exists, it should predict what a person should respond, or how a person should respond on each of these 5 items of our assessment. And so we put it in a regression statement, where we're predicting a person's item response based on their factors. Right, so F is subject S's factor score. Again, it can be anything. Pick a range. Maybe it has anyone like a mean of 0? Nah, that's not good. Mean of 100. Make it like an IQ. I've always heard of people playing the lottery. Ever heard that? This is bad. It's like it's like a tax on the people who can't do math, right? So this is like IQ if you're gambling. Never mind. I shouldn't say that. I waste my money all the time on gambling. My gambling now is more like, stock market, which is just as much gambling, right? So anyway, we have our factor here, and we plug a score in, and we say, okay, let's predict what the actual score for this item would be. So this is like this is someone's score on. Let's imagine the first item. I think about gambling a lot. I think that's what the first one was. What this regression equation says, okay, if you have a factor score of this, we plug it into this regression. We've estimated an intercept, which looks like a mu here. We've estimated a beta weight, which actually we call a factor loading here. And we have these two things combined to give us your predicted score. And then we have error off on the outside of it. And that error should tell us how far off we are from your actual score. And we can quantify it. Riveting, right? So you've seen regression before. We've done regression this whole class. A factor model is a regression where the independent variable in it is unobserved. Right? It's like you just have missing data, or you just didn't collect that data. It's not there. So I'm going to stop there. We're up at a break. Take 10 minutes. We'll come back and we'll hear some more fun things about things we can't observe.